Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The Calculating Prodigy, a room in Rouen, France, circa 1642. The air is thick with the scent of metal filings and oil, a sharp counterpoint to the musty odor of parchment and ink. Here a young man, still a teenager, hunches over a complex assembly of gears, dials and levers. Blaise Pascal is attempting something audacious, something that borders on the Promethean for his era. He is building a machine to perform a function of the rational mind. He is endeavoring to mechanize arithmetic itself. This device, which would come to be known as the Pascaline, was born from a very practical, almost mundane, source of filial devotion and intellectual frustration. His father, Etienne Pascal, a respected mathematician in his own right, had been appointed a tax supervisor for Upper Normandy by Cardinal Richelieu. The position was a torrent of numbers, an endless sea of additions and subtractions, of livres, sols and deniers, that had to be tallied with painstaking precision. The daily spectacle of his father's exhaustion, buried under mountains of ledgers, spurred the young Pascal to action. He witnessed firsthand the colossal labor involved, a form of intellectual servitude that consumed hours and was perpetually vulnerable to human error. A single misplaced digit, a moment of lapsed concentration, could cascade into significant miscalculations, affecting the fortunes of the French crown and its subjects. The existing tools, like the abacus, required constant manual manipulation and offered little in the way of automated verification. Pascal's vision was for a machine that would internalize the logic of calculation, an automaton for sums that would work with unerring mechanical certainty. He began the project at the age of 19, and it would consume him for the better part of a decade. He produced some 50 prototypes, each a refinement upon the last, each a testament to his relentless perfectionism. The fundamental challenge was immense. While representing digits with toothed wheels was a relatively straightforward concept, a wheel with 10 teeth could represent the numbers 0 through 9. The true difficulty lay in mechanizing the carry operation. When a column of figures in manual addition sums to 10 or more, a digit is carried over to the next column to the left. Replicating this cascading sequential process in a physical apparatus of brass and wood was a profound engineering puzzle that had thwarted previous ambitions. The resulting machine was a marvel of 17th-century ingenuity. Housed within a small, elegant box, the Pascaline presented the user with a series of metal wheels, each marked with the digits 0 to 9. To perform an addition, the operator would insert a small stylus into the corresponding slot for each digit of a number and rotate the wheel until the stylus hit a fixed stop. The cumulative sum would appear in a row of small windows at the top of the box. Subtraction was accomplished through a more complex method utilizing 9's complements, a clever arithmetic trick that the machine's design accommodated. The genius of the Pascaline, the very heart of its innovation, was a mechanism Pascal called the sautoir, or kicker. This was his elegant solution to the carry problem. Connected to each numeral wheel was a small weighted pawl. As a given wheel turned from 9 back to 0, a pin on that wheel would lift the sautoir of the adjacent higher value wheel. Upon clearing the pin, the weight of the sautoir itself would cause it to drop, kicking the next wheel forward by precisely 1/10 of a revolution, thus registering the carried digit. This action would then prime the next sautoir in the sequence, allowing for carries to propagate automatically across the entire accumulator. This was a sophisticated, gravity-assisted system that ensured a clean and reliable transfer of value from one place to the next. Earlier calculating devices, like the one conceived by Wilhelm Schickard, 2 decades prior, employed a more fragile system of mutilated gears that were prone to jamming if a carry needed to propagate across several digits simultaneously, for example, when adding 1 to 999. Pascal's sautoir was a far more robust and scalable solution. The Pascaline was, in essence, a physical argument. It was a demonstration, in polished brass, that a process of human reason could be mapped onto the predictable deterministic motions of a machine. It was a device that freed the intellect for higher pursuits, for the formulation of theories and the discovery of principles, by delegating the drudgery of computation to a clockwork assistant. Pascal himself wrote of its purpose, suggesting it would relieve the operator of the labor that so often fatigues the spirit. The invention earned him a royal privilege in 1649, a document that functioned as an early form of patent, granting him the exclusive right to design and manufacture calculating machines in France. Despite its technical brilliance and the royal endorsement, the Pascaline was a commercial disappointment. The machines were expensive to produce, requiring the skill of master clockmakers, and they were delicate. Their very precision made them susceptible to damage from rough handling. Furthermore, the professional clerks and accountants of the day, a guild whose livelihood depended on their specialized arithmetic skills, viewed the device with a certain suspicion, perhaps sensing in its gears a faint premonition of their own obsolescence. A few dozen were built, sold to wealthy nobles, scientists, and government officials, becoming more of an impressive curiosity than a ubiquitous tool. Yet its historical significance resonates far beyond its market performance. The Pascaline stands as a foundational monument in the long history of automatic computation. It is a direct ancestor to the mechanical calculators of Leibniz and Babbage, and through them, to the entire digital world we inhabit today. It embodied the crucial insight that logic has a physical architecture, that a sequence of thought can be translated into a sequence of interlocking parts. This conquest of the finite, this mastery over the discrete and countable world of numbers through mechanical means, marked the triumphant conclusion of Pascal's first great intellectual chapter. His mind, having tamed the toil of arithmetic, was already turning toward new, more profound mysteries, away from the solid certainty of gears that fill a space, and toward the very nature of space itself, its geometric properties, and the deeply controversial possibility of its absolute emptiness. The intellectual journey from the tangible world of cogs and levers to the ethereal realm of the absolute void represents a profound pivot in scientific thought. Blaise Pascal, having mechanized the process of calculation, now directed his formidable intellect toward one of the most fiercely contested philosophical questions of his era, the existence of nothingness. For nearly 2 millennia, Western science had been dominated by the Aristotelian dictum of horror vacui, the principle that nature abhors a vacuum. This was an idea woven into the very fabric of physical understanding, suggesting that any attempt to create a true void would be met by the immediate and violent rush of matter to fill it. It was a universe where emptiness was a logical impossibility. This ancient certainty was thrown into disarray in 1643 by the work of Evangelista Torricelli, a disciple of Galileo. In a simple yet revolutionary experiment, Torricelli filled a long glass tube with mercury, sealed one end, and inverted it into a basin of the same liquid. The mercury column in the tube fell, but only to a certain height, leaving a space at the top of the sealed tube. The question that electrified the scientific community of Europe was immediate and profound. What resided in that space? Was it a subtle vapor of mercury, an imperceptible ether, or was it, as Torricelli himself dared to suggest, an actual vacuum, a pocket of pure emptiness? The Torricellian experiment produced a phenomenon. It fell to Pascal to definitively explain its cause. Upon learning of these experiments, Pascal began his own meticulous investigations, first in Rouen and later in Paris. He replicated Torricelli's work with various liquids and tube shapes, confirming the basic results with an artisan's precision. His genius, however, lay in formulating the decisive hypothesis. He proposed that humanity lives at the bottom of a vast ocean of air, a fluid with substance and weight. It was this atmospheric pressure, this immense column of air pressing down upon the mercury in the basin, that supported the column of mercury inside the tube. The space at the top of the tube was empty because the weight of the air was insufficient to push the heavy liquid all the way to the top. This was a beautifully simple and powerful physical model. It transformed the philosophical puzzle of the void into a question of mechanics and measurement. And like any good scientific theory, it yielded a testable prediction. If the air had weight, then its pressure must decrease with altitude. A barometer carried up a mountain should therefore show a lower column of mercury than one that remained at the base. The difference in height would be a direct measure of the weight of the air between the two elevations. In 1648, Pascal orchestrated one of the most elegant and conclusive experiments in the history of science. His own delicate health prevented him from undertaking the arduous task himself, so he entrusted the execution to his brother-in-law, Florin Perrier, a councillor in Clermont-Ferrand. The chosen location was the Puy des Dômes, a large volcanic dome rising over 1,000 meters above the town. Pascal's instructions to Perrier were a model of scientific rigor. 2 identical mercury barometers were to be prepared. One would be left at the base of the mountain, in the care of a trusted observer. The other would be carried to the summit. On the morning of September 19th, Perrier, accompanied by a small group of distinguished local citizens to act as impartial witnesses, began the ascent. At the summit, they assembled the second barometer and observed the result. It was immediate and dramatic. The mercury column stood more than 3 inches lower than in the identical instrument at the base. As Perrier recorded in his detailed report to Pascal, the observers were so struck with astonishment and admiration that they repeated the measurement several times in different locations on the summit, always with the same outcome. The descent confirmed the finding. As the party returned to the base, the mercury in their barometer rose again until it perfectly matched the level of the stationary instrument. The Puy des Dômes experiment was a masterpiece. It provided irrefutable proof that the column of mercury was supported by atmospheric pressure. The weight of the air was a measurable physical quantity, and the Torricellian space was indeed a vacuum. Pascal's work demolished the ancient doctrine of horror vacui and established the foundations of hydrostatics and meteorology. In his subsequent publication, Récit de la grande expérience de l'équilibre des liqueurs, he detailed the results and their implications, laying out a comprehensive theory of fluid pressure. His triumph was so complete that the modern international unit of pressure, the Pascal, is named in his honor, a lasting tribute to the man who weighed the air. While his mind was occupied with the physics of atmospheric pressure and the reality of empty space, another part of his intellect was exploring the abstract properties of space itself. At the astonishing age of 16, Pascal had composed a work of pure mathematics that was in its own way as revolutionary as his later experiments. This was his essay on conics, a brief but extraordinarily dense treatise on the geometry of conic sections, the ellipse, the parabola, and the hyperbola. The work built upon the pioneering, though then obscure, ideas of Gerard Desargues, who had begun to investigate the properties of geometric figures that are preserved under projection. The centerpiece of this essay was a single, powerful theorem of breathtaking elegance and generality, which came to be known as Pascal's theorem, or the hexagrammum mysticum. The theorem states that if one takes any 6 arbitrary points on any conic section and joins them to form a hexagon, the 3 pairs of opposite sides will intersect at 3 points that lie on a single straight line. This line is now called the Pascal line. This discovery reveals a hidden, almost magical coherence within these fundamental curves. It is a theorem of pure position and incidence, a property that holds true regardless of how the conic or the hexagon is stretched or distorted. It belongs to the world of projective geometry, a system where the parallel lines of Euclidean space are understood to meet at a point at infinity. Pascal's work on conics demonstrated a geometric intuition of the highest order. He had grasped a deep structural truth about the universe of shapes, a truth that transcended the metric properties of length and angle. This youthful achievement, circulated in manuscript and praised by intellectual giants like Descartes and Mersenne, marked him as a geometer of the first rank. Having established the physical reality of the vacuum with a mountaintop experiment, he simultaneously charted the abstract realities of geometric space with a theorem of profound beauty. From the certainty of geometric theorems and the measurable weight of the air, his focus would soon shift to a domain that seemed to defy all rational analysis: the unpredictable roll of the dice. The intellectual currents of the mid-17th century flowed toward certainty. Descartes sought indubitable foundations for knowledge. Geometers like Pascal himself explored the immutable truths of conic sections. Yet a vast and turbulent ocean of human experience remained uncharted by reason, the realm of chance. For millennia, the fall of dice and the turn of a card were seen as the province of fortune, fate, or divine whim, a chaotic domain where calculation was futile. The salons and gambling dens of Paris, however, harbored questions that were both practical and profound. It was from this world of high-stakes leisure that a challenge emerged, one that would compel Pascal to apply his formidable intellect to the very structure of uncertainty. The specific puzzle, posed to Pascal by the worldly intellectual and gambler Antoine Gombault, Chevalier de Marais, was the problem of points. Imagine 2 skilled players engaged in a game of chance for a set prize. The first to win a certain number of rounds takes the entire pot. The game, however, is interrupted before either has reached the target. How should the stakes be divided fairly based on the score at the moment of interruption? The question had circulated for centuries, a persistent thorn in the side of mathematicians who had attempted solutions and failed. The intuitive answers were always flawed. A simple division based on the ratio of points won so far, for instance, fails to account for the number of points still needed to secure victory. A new kind of thinking was required. This intellectual catalyst sparked one of the most fruitful correspondences in the history of science. In the summer of 1654, a series of letters began to travel between Pascal in Paris and the brilliant lawyer and mathematician Pierre de Fermat in Toulouse. Through this exchange, these 2 minds, working in concert yet with distinct methods, gave birth to the mathematical theory of probability. They transformed the analysis of gambling from a gambler's hunch into a rigorous branch of mathematics. Fermat approached the problem with his mastery of algebraic enumeration, exhaustively listing possibilities. Pascal, drawing on his deep intuition for combinatorial structures, developed a more elegant and generalizable method. His primary instrument was a configuration of numbers he explored in his treatise, the Traité du triangle arithmétique. While this array, now universally known as Pascal's triangle, had appeared in various forms in Chinese, Indian, and Persian mathematics for centuries, Pascal was the one who systematically plumbed its depths and revealed its profound connection to combinatorial theory. The triangle is an infinite symmetrical arrangement of numbers. It begins with a single 1 at the apex. Each subsequent number is the sum of the 2 numbers directly above it. The rows of this triangle, it turns out, contain the binomial coefficients, the very numbers that answer the question, how many ways can one choose k items from a set of n items? This value, n choose k, appears in the triangle, and with it, Pascal held the key to counting complex possibilities. To solve the problem of points, Pascal imagined all the possible ways the game could have finished had it continued. Suppose player A needs 2 more points to win, and player B needs 3. Pascal reasoned that the game would be decided, at most, in 4 more rounds. Why 4? Because after 4 rounds, one player is guaranteed to have won. The sequence of wins and losses over these 4 hypothetical rounds determines the victor. Using his triangle, Pascal could precisely calculate the number of sequences that would lead to a victory for player A versus the number that would lead to a victory for player B. There are 16 possible outcomes for 4 rounds, each as likely as the other. Pascal could show how many of these 16 futures belong to player A and how many to player B. The stakes, he argued, should be divided in exactly that proportion. It was a solution of stunning clarity and power, reducing a seemingly intractable problem of fairness to a matter of systematic counting. The analysis, however, yielded a far more fundamental concept. In calculating the fair division of the stakes, Pascal implicitly formulated the idea of what we now call expected value. He recognized that the present value of a gamble is a weighted average of all its possible future outcomes. It is the sum of each potential prize multiplied by its respective probability of occurring. If you have a 1/2 chance of winning 100 francs, the expectation, or the fair value of that ticket, is 50 francs. This principle, which he termed l'espérance mathématique, was a monumental intellectual leap. It provided for the first time a rational method for comparing different risky propositions and making decisions under uncertainty. The world of chance now had its own arithmetic, its own logic. It was a geometry of the future, a way of measuring what was yet to be. The implications of this breakthrough radiated outward, far beyond the gaming tables of Paris. The Pascal-Fermat correspondence established the mathematical foundations for probability and statistics, disciplines that have become indispensable to the entire edifice of modern science and commerce. The tools they forged are now fundamental to the actuarial science that underpins the insurance industry, allowing for the calculation of risk across vast populations. They are essential to financial modeling, where the valuation of assets depends on probabilistic forecasts of future earnings. In physics, the probabilistic nature of quantum mechanics describes the universe at its most fundamental level, where the position of a particle is a cloud of probabilities until it is measured. From the design of clinical trials in medicine to the algorithms that power machine learning and artificial intelligence, the logic of chance, first articulated by Pascal, governs our attempts to find patterns in chaos and make reasoned choices in the face of an unpredictable world. Having brought the light of reason to the weight of the air and the roll of the dice, Pascal had developed a powerful new way of thinking about the unknown. He had demonstrated that even where certainty is impossible, rational analysis can provide a guide for action. This very intellectual framework, forged to determine the fair price of a lottery ticket, would soon be turned toward a question of infinitely greater stakes, a wager concerning the ultimate nature of human existence and its place in the cosmos. The catalyst for this profound reorientation of intellect arrived with the force of revelation. On the night of November 23rd, 1654, Blaise Pascal experienced a private, intense spiritual event, a night of fire that he secretly documented on a piece of parchment and sewed into the lining of his coat, keeping it with him for the remainder of his life. This document, his memorial, speaks of certitude, feeling, joy, peace. From this moment forward, The brilliant mind that had plumbed the nature of the vacuum and codified the logic of chance would dedicate its formidable powers to the architecture of faith and the anatomy of the human soul. The intellectual tools honed on problems of physics and games of fortune were now aimed at the ultimate uncertainty, the question of God and humanity's place in the infinite. He entered a philosophical landscape defined by two powerful, opposing currents. On one side stood the triumphant rationalism of figures like René Descartes, who sought to build a system of knowledge from the ground up on the bedrock of indubitable reason, a clockwork universe accessible to the human mind. On the other side lingered the pervasive skepticism of Michel de Montaigne, who questioned the very capacity of reason to arrive at stable, universal truths, emphasizing instead the contradictory and fickle nature of human experience. Pascal's ambition was to forge a path through this intellectual schism. He would employ reason to its absolute fullest capacity, yet he would do so to demonstrate its inherent limitations and to map the terrain that lay beyond its reach, a domain accessible through a different kind of human faculty. His final great work, the Pensées, or Thoughts, embodies this project in its very form. Left unfinished at his death and published posthumously from a chaos of bundled notes, the book is a collection of fragments, aphorisms, extended arguments, psychological portraits, and raw observations. It was intended as a grand apology for the Christian religion, a defense aimed at the sophisticated, worldly unbeliever of his age. The fragmented nature of the text, far from being a weakness, contributes to its enduring power. It reads like an intimate intellectual journal, capturing the mind in the very act of wrestling with the paradoxes of the human condition. Our greatness and our wretchedness, our capacity for infinite understanding, and our immersion in trivial diversions. Within this constellation of brilliant fragments lies the argument for which Pascal is most widely remembered, a piece of reasoning so audacious it continues to provoke debate centuries later. Known as Pascal's wager, it represents the ultimate application of his work on probability to the domain of metaphysics. The argument itself is a masterpiece of rhetorical framing and logical force. It begins by acknowledging reason's silence on the ultimate question. Through logic and science, we can measure the world, but we are unable to prove or disprove the existence of God. As he writes, we are embarked. We are already in the game, and a choice is unavoidable. To abstain from choosing is itself a choice. Having established the necessity of a decision, Pascal lays out the problem in the precise terms of a game of chance, one with the highest possible stakes. He presents a simple decision matrix. One can wager for the existence of God, or one can wager against it. The core of the argument rests on an analysis of the potential outcomes, using the same principle of expected value that he and Fermat had developed to divide the stakes in an interrupted game. Consider the wager for God. If the believer is correct and God exists, the reward is an eternity of bliss, a gain of infinite value. If the believer is wrong, the loss is the forfeiture of certain finite worldly pleasures during a finite life. The cost is finite. Now consider the wager against God. If the non-believer is correct, the gain is the enjoyment of those same worldly pleasures, a finite reward. If the non-believer is wrong, the loss is eternal damnation, a loss of infinite value. The mathematical logic as Pascal saw it is inexorable. Even if the probability of God's existence is exceedingly small, a small, finite probability multiplied by an infinite payoff yields an infinite expected value. Any course of action with an infinite expected gain overwhelms any alternative that offers only finite gains or losses. Therefore, the only rational choice, when viewed through the cold calculus of probability,
is to wager on God. The argument's genius lies in its strategic pivot. It reframes the debate, moving from a quest for evidence to a problem of rational decision-making under radical uncertainty. It is a pragmatic argument designed to compel action, to encourage the skeptic to take the first step by adopting the habits of belief, in the hope that genuine faith will follow. The conclusion of this intellectual journey reveals a remarkable and indivisible mind. The same impulse that drove him to build a machine to relieve the drudgery of arithmetic also drove him to chart the pressure of the atmosphere, to dispel ancient errors about the nature of a vacuum. The same analytical clarity that allowed him to found the calculus of probabilities for gamblers also informed his final profound meditation on the ultimate gamble. The gears of his calculating machine, the column of mercury in his barometer, the distribution of stakes in a game of chance, and the existential wager for an eternal soul all appear as expressions of a singular, lifelong project, the relentless application of reason to confront and systematize the unknown. Pascal's work stands as a permanent monument to the vast scope of human intellect. He demonstrated that the rigor of mathematical thought could be a powerful tool for navigating a world of contingency and chance. His legacy is the powerful demonstration that this same intellectual architecture provides a profound framework for contemplating the very conditions of our existence. He explored the frightening silence of infinite spaces with the same courage and precision he brought to the role of a die, leaving for posterity a universe where the mechanics of reason and the mysteries of the human heart are perpetually and beautifully intertwined.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.